This is section 12.3, Conditional Probability. When we're looking at independent events, these are events that can be either simple or compound. A simple event is rolling a 5 on a die. A compound event is rolling a 5 on a die and drawing a 2 from a standard deck of cards. So something that's compound, you're actually doing more than one thing. Something that's simple, you're just doing one thing. In example 1, it says in a board game, 3 dice are rolled to determine the number of moves for the players. What is the probability that the first die shows a 6, the second die shows a 6, and the third die does not? So first we have to think about the probability of each of these individual events. And we know that if we have one die that's rolled and we get a 6, the probability of that happening is 1 over 6 because there's only 1 6 on the dice. So we have 1/6 for our first probability. It also says the second die shows a 6. Well, this is nothing to do with the first one, still just using a die, and there's going to be 1/6 that this one would be a 6. And then the probability that the third die does not. So there's 5 other numbers on the die that aren't 6, so there's 5/6 of a chance of it not being a 6. So with these, we're actually going to be multiplying these together to get our final answer. And when we do that, we're going to get 5 over 216 as our final probability. A dependent event is when one outcome affects another outcome. So in our last example, whatever we rolled on one die didn't affect what we rolled on the other one. But then there are some events that are dependent. One thing affects the other. An example of that is drawing 2 cards from a standard deck without replacing the first card. So if I draw, say, a king of hearts the first time and don't replace it, then on the second time there's no way I'm going to draw a king of hearts. So the second event is dependent on the first event. In example 2, it says a bag contains 12 red, 9 blue, 11 yellow, and 8 green marbles. 3 marbles are drawn at random from the bag one at a time and not replaced. Find the probability that red, blue, and green marbles are selected in order. So first let's go ahead and think about how many total marbles there are. And if we add all of the marbles together, we know that there's going to be a total of 40 marbles. So for the first one, it says find the probability that red, right here, says that red is drawn, and it says that there's 12 red. So the probability of that happening is 12 over 40. All right, now we have to think of the probability that a blue is going to get drawn. Well, in this case, there's 9 blue. No blues have been taken out yet, so we know for sure that there's 9 chances that it could be blue. Now, here's where it's a little bit tricky. Originally, we started off with 40 marbles, but we took one out already. We took a red one out, and so there's 1 less marble. So we're going to actually have to say that now there's 39 marbles. Okay, let's move on. Now it's saying we're going to select a green marble. Well, again, a green marble hasn't been selected yet, so there's 8 that we could choose from. But again, now there's 2 marbles missing, so we're going to have to change that bottom number to a 38. And now it's the exact same process as we did before. We're just going to multiply. And when we multiply, we're also going to need to do some simplifying. And when we simplify, multiply, and simplify, we're going to end up with 18 over 1,235 for our final answer. Conditional probability is the probability of one event given that another event has already occurred. And we actually have a formula that we're going to use for this. So conditional probability, given that A and B are dependent events, they're depending on one another, the conditional probability of an event B, given that event A has already occurred, is defined as the probability of A and B divided by the probability of A, where the probability of A cannot equal 0. In our example, it says that Carolina rolls a 6-sided die. What is the probability that she has rolled a 3, given that she has rolled an odd number? So first we're going to look at defining A and B in this case. So we're going to go ahead and say that A is the probability that she rolled an odd number. because we know that she rolled an odd number, but we also are trying to find that probability that it's a 3. So we have these two things that we're coming up with. So we know that the probability of it being an odd number, so the probability of A, well, there's 3 odd numbers, so that's going to be 3 over 6, or 1/2. For it to be a 3, we know that the probability of it being a 3, so first it would have to be probability of A and B, so the probability of it being odd, and 3 is 1/6. Because there's 6 sides on a dice, only one of them is a 3. So now we're just going to go ahead and plug these into our formula. So we have the probability of A and B on top, and the probability of A and B is 1/6 divided by the probability of A, and in this case that's 1/2. So we have 1/6 divided by 1/2, and that's going to give us 1/3. A contingency table organizes observed frequencies of outcomes into categories according to 2 variables. So we're still going to be using the same formula that we used in the last slide, but now the information is organized into a table. Example 2 says define the probability that a test subject stayed healthy given that he or she used an experimental drug. And we have this chart that we're looking at, and we see that we can look at sick patients, healthy patients, and we can also see, are they sick and they used a drug, or are they sick and they used a placebo? Are they healthy and they used the drug, and healthy and they used the placebo? So, given what it says, we're going to want to find the probability of H given that D occurs. So we're going to go ahead and write this out. The probability of H given D happens. So remember, with our formula, we're going to have the probability of H and D divided by the probability of D. So let's go ahead and find that probability of H and D. So the probability of H and D, we're going to be looking right here on our table because that goes with H and D, so that's going to be 800. And we have to know how many people are there. And if we add up all 4 of the areas on the chart, we're going to get that there are 4,000 total people. And now we also have to figure out just the probability of D. And if we look at all of the people in D, so that's 1,600 plus 800, that's going to give us 2,400 over 4,000. So now we can go ahead and plug all of this into our formula. So we have the probability of H and D, which in this case we found out was 800 over 4,000. We're going to plug that in. 800 over 4,000. And then we're going to divide by the probability of D, which in this case is 2,400 divided by 4,000. And if we go ahead and simplify all of this, that's going to give us 1/3. So the probability that a subject stayed healthy given that he or she used the drug is 1/3. Contingency tables can also present relative frequencies of outcomes, which are ratios of the number of observed outcomes in a category to the total number of observed outcomes. In example 3, it says that the table shows the number of students who are varsity athletes. Find the probability that a student is a varsity athlete given he or she is a junior. So given that information, we're going to be finding the probability that it's a varsity athlete given that they are a junior. So remember, when we do this using our formula, we're going to have the probability of V and J over the probability of J. So now we have to figure out what each of these are. So the probability that the person is a varsity and a junior is 0.03. And we actually pulled that directly from the table. Varsity junior is 0.03. Then the other information we need is that the probability that they're a junior. So then the probability for junior, we have two areas that are junior, so we're going to add those together. So we have 0.03 plus 0.23, and that's going to give us 0.26. So now we can go ahead and plug those into our final formula. So we're just going to have 0.03 divided by 0.26, and that's going to give me 11.5% for the final answer.